All right, everybody. Thank you for coming. Please welcome Dr. Allison Lange. She's the R&D molecular biologist at Omega Yeast in Chicago. She graduated from Dartmouth College with a degree in genetics, cell and developmental biology, and was awarded her PhD in biochemistry from Emory University. Allison then brewed professionally for 9 years in Washington, D.C. area. She began as a brewer and beer scientist at Port City Brewing Company, then moved on to be director of brewing operations, lead brewer, lead QC, and lead cellar person at 3 Star Brewery. Most recently, she was head brewer at Old Ox Brewery. Please welcome Dr. Allison Lange.
Hey, everybody. Like you said, my name's Allison. I work for Omega Yeast. We are based... Is that the air conditioner or is that microphone feedback? What do you guys think?
Air conditioner.
All right, sweet. Just checking. We're based out of Chicago, but we ship everywhere, and I have talked to a lot of you guys about how you use our yeast, and I really appreciate that. Today we're going to be talking about enzymes. So we're going to start off by talking about just background on enzymes. What are they? How do they work? The basic biology of it. I think a lot of times when we think about enzymes in the brewing world, we think about some liquid that comes in a bottle, but don't really think about what those enzymes are doing on a molecular level. So we'll start out there. We'll go through some of the enzymes that you use in mashing, go through enzymes used during fermentation, and then go through some conclusions. So that's how things will be organized today. So first thing is, what is an enzyme? Enzymes are proteins that catalyze biological reactions. All catalyze means is that they increase the rate of those reactions. They are specific to the kind of reaction that they do. So a particular enzyme will have a particular substrate, that's the thing that it acts upon, and it will do a particular reaction. One of the key things is that it's not consumed during that reaction and is unchanged at the end of it. So the way that generally works is you have a protein that has a binding pocket for its substrate. It will then often change shape a little bit in order to facilitate whatever reaction it's going to do. And in this case, you're taking a substrate and then breaking it into 2 different products. There also are enzymes that would do the opposite. So we would put this orange one and this blue one back together into this green one. So obviously, we're not just these little semicircular blobs. This is a crystal structure of an example of an enzyme and what it actually looks like. This is a kinase, so it takes a phosphate and it attaches it to something else. And you can see here in blue, that's what the binding pocket looks like when it doesn't have its product in it, or it doesn't have its substrate in it. But then when the substrate actually binds to it, you can see that the enzyme actually changes shape. And that's involved in actually reducing the activation energy. So that actually helps to facilitate that phosphate transfer. So by changing its shape, it actually can make that reaction go faster. And that's one of the main ways that enzymes work. So, what is this activation and energy that I'm talking about? It's the energy that it takes in order to do whatever the reaction is. So you can see, this is just an example. If I was, for example, trying to put 2 things together, it takes a lot of energy and a lot of time for that to happen on its own. But if you have an enzyme that's actually facilitating that, then you have a much lower activation energy, and it makes that reaction much more likely to happen, which is what catalyzing is. So the mechanism for that I've kind of alluded to. One of the ways it can happen is just by putting 2 substrates close to each other, because it increases the likelihood. One way is it can act as a template or a scaffold. And so basically it holds your 2 different products together so that they actually can do their reaction. The last thing is that it can potentially have providing a different kind of environment. So you can provide a microenvironment that has the right pH or things like that to facilitate this reaction. So lots of different ways to mess an enzyme up or to promote its activity. These are things that are important when we're trying to make sure to decide when to apply an enzyme at the right time, or to provide favorable environment for our enzymes, like in the mash, for example. Enzymes need an optimal pH, they need an optimal temperature, they need time to react. The substrate concentration, so the thing that it's actually working on, affects how fast that it goes. The enzyme concentration itself can affect how fast it goes. And then there's also things like inhibitors, activators, or cofactors that are involved in how your enzyme is working. Sometimes that can take advantage of that pocket that I showed you. So you have, for example, an inhibitor that can bind in the pocket, change the shape of the enzyme, and prevent the actual substrate from getting in there. That's one thing you have to look out for. Sometimes there are different trace metals that are involved, or for example, calcium is a big one that you guys are probably familiar with in the mash. That calcium can be a cofactor for some of these, and you have to have appropriate levels of calcium ions in your mash in order for certain enzymes to work. Some of the big ones that are important for us are pH and temperature especially. The main reason for that is that if you get way outside the optimal range for pH or temperature, then you denature your enzymes. All denaturing means is making your folded protein unfold. This is useful, this is not. That spaghetti doesn't do anything for you. Protein structure itself has 4 different levels. So we talk about primary, secondary, tertiary, and quaternary structure. The primary structure is just the sequence of amino acids. So that's just kind of the order of all the amino acids that are out there. Again, that's the spaghetti, that's not doing anything for you. That then organizes itself into secondary structure. Some of the more common ones there are alpha helices and beta sheets. It's actually pretty cool. Amino acids will organize themselves into helices, and then those form together to form the protein. Once those things interact, that's called tertiary structure. That's kind of your final form if you have a one protein enzyme. And then quaternary protein structure is when you have multiple pieces that all interlock in order to form one big piece. All of these different interactions have different kinds of bonds that are involved in them. So there are some that are really, really strong. Those are the covalent bonds. That's the kind of thing that you have between different amino acids. There's more weak bonds that are involved in like making these helices, for example. They're often there's hydrogen bonds and then also ionic bonds or different kinds of disulfide bridges. Doesn't really matter the details of them. What's important there is that they're weak and they're easy to disrupt. And so that's what happens when you have a bad, when you're outside your pH range or your temperature range. Those weak bonds tend to get broken, and that's why your protein denatures. There are lots of different kinds of enzymes. This is the general categories. They tend to be named after the reaction that they do, and then they have ACE on the end of them. So this is all the ones that exist in the world. So transferases, lyases, isomerases, ligases, and they do various things. So they put things together, they take things apart, they can transport ions, they can do all kinds of different things. Ones that are relevant in brewing are some of these ones that I've highlighted over here on the right. So in the brewing world, we have enzymes from all different kinds of categories. Some that I'm sure you're familiar with are things like glucose oxidase, which is involved in reducing ABV in some of the NABLAB beers. A ton of hydrolases. That's ones like all of our amylases and proteases, xylanases, glucanases, all those kind of things. So things that are breaking down all those starches into sugars. We'll go through kind of the details of those later, but ones that we're really familiar with mashing. Lyases, I don't actually know the origin of the word. I've always associated with lysis and the idea of breaking something down or degradation. So these are things that cleave things in a way that's not through hydrolysis. So things like beta lyases involved in thiolizing and ALDCs that are involved in prevention of diacetyl. Both of those are lyases. Isomerases, I think we're most familiar with the idea of iso-alpha acids. It's just like flipping two different atoms in a molecule. That's what an isomerase does. And things like translocases. So the idea of getting sugars into cells, translocases are involved in that. So how do I use enzymes if I'm a brewer? You use enzymes all the time. There are the ones that are inherent to the brewing process. So there's ones that you can just tweak the conditions of your brew in order to affect their performance. Those, for example, are all of the enzymes I was alluding to in mashing. So all of those amylases that are involved in creating sugars. Things like hop creep. So when you add hops, you bring along enzymes that then restart fermentation. Or things like diastatic yeast. So the STA enzyme is one that breaks off glucose molecules, and that's one that we're really familiar with. There's also ones that you add exogenously. All exogenous means is that it's outside the system. So it's something that you're adding that wasn't already there. Examples of those are things like the enzymes you buy, the things that we were talking about coming in a bottle. things like amyloglucosidase or glucanase, things like that. There's also enzymes that have been added to yeast. Those are kind of funny because they are exogenous to the system, because you're putting them there, because they ordinarily ALDC wouldn't have gone into your beer if you hadn't have, chosen that specific yeast. Something to understand is that it's actually endogenous to the yeast, because we put it inside there. And so it's endogenous to that yeast system, but exogenous to the whole brewing system. And I only bring that up because I tend to use those words, and I just kind of wanted to clarify what that means. So where do you get these enzymes that come in these bottles? This was something that was kind of new to me. I didn't use a lot of enzymes when I was in the brewing world, but I've gotten a lot more familiar with it. So I didn't know some of these major manufacturers. Places to look if you're interested in learning more about enzymes, or if you want to buy them and kind of see what's out there. I'd recommend some of these bigger ones, DSM, Carey, AB Vickers. Also take a look at your major craft beer suppliers. Things like Roar BSG, Country Malt, Gusmer. Murphy & Sons is here. Their website is spectacular. They have a whole outline of all kinds of different products you can use. They're also going to be giving a talk on enzymes tomorrow, and specifically with the idea of using them to improve your cost of goods. So check their stuff out. I just figured out they were having this talk. This was not planned at all, but it should be a good talk. Or take a look at yeast suppliers. So we obviously specialize in the enzymes that are produced by yeast that we have genetically modified. But then also lots of yeast providers also provide enzymes that you can buy. And a lot of that is because we have expertise in microbiology. And as we'll get into in just a second, a lot of the source for enzymes are purification from things like yeast or bacteria. So how do these companies get these enzymes? There's three major sources. You can either purify it from the original source that we're used to, so something like barley, we all know it comes along with its own amylases to break down the starches in its cell. So you can do that. It's not particularly efficient because you have to grow this plant and then break it down. There's all kinds of other material other than these enzymes. So what tends to happen instead is that you have some sort of genetic modification where you actually get you code for the DNA that codes for the enzyme is actually put into a bacteria, and then you basically use the bacteria as a big enzyme production factory. That's the most common. Or there are bacteria that natively make a lot of these enzymes. So it's things where we're taking advantage of a natural system that already exists and growing up those bacteria. In any case, those cells get grown up in large volume and then get mechanically broken open through a lysis step. There's lots of different buffers and different kind of protease inhibitors and stabilizers that go into that process. They then get purified, and here we have just a drawing on a small scale of things like centrifugation or chromatography or dialysis. Those kind of ideas are what are used for purifying proteins, though obviously on a commercial scale, it's on a way bigger scale. So think about these pictures as kind of like the homebrew version of what's going on when you purify a protein. Once it's purified, then it also goes through a lot of analysis. So using things like mass spec or NMR or X-ray crystallography, you can verify you have the right enzyme and that it's actually pure. Some examples of where different enzymes come from, just to kind of give you an idea. Alpha amylase, for example, you can purify from Bacillus subtilis or Aspergillus, a couple of different natural bacteria that are out there. Beta amylase comes from Bacillus, proteases come from Aspergillus. So all of these things are naturally occurring, and we just take advantage of the systems that were already out there. Cool, so now we're going to move on and talk about some of the enzymes that are used during mashing. Obviously, there are a ton of different enzymes that are involved that we're actually creating a nice environment for. We use enzymes to control the fermentability, so we can just determine how dry or sweet a beer is, increase our extraction, improve our filtration, increase our fan, reduce haze, and then aid in head retention. And we're going to go through some of the enzymes that are involved in all those processes. So the first ones are the ones that are involved in saccharification. These are the ones where the main ones that are happening during the mash. The major ones are alpha amylase, beta amylase, and limit dextrinase. I'm sure those of us that started out at homebrewers all all read How to Brew by John Palmer, and just want to thank him for this analogy here. But I kind of think about these as either a chainsaw, a wood chipper, or a pole saw. So they kind of cut up all of the different long chain sugars in different ways, and then they have different results. So they result in having a different mix of sugars, and then also have different effects on how your mash goes. So either focusing on your extraction efficiency or your fermentability, and determining sort of how fermentable your wort is. So these are our kind of three major enzymes, and we've got this tree analogy, and we have these long chain sugars. Your amylase, I kind of think of as a chainsaw, so it can cut anywhere. And it ends up with all kinds of fragments of different sizes. Your beta amylase is kind of like a wood chipper, so it chews from the ends and creates freeze maltoses from the ends as it kind of chomps along the sugars. And then limit dextrinase is kind of like a pole saw, so it trims off branches. So it will break between long branches, and you end up with these long chain sugars. Obviously, the way that we manipulate these kind of things and tweak them in the brewing process is by choosing the temperature that we mash at. So if you're on the lower end of the spectrum, you're favoring beta amylase. So you get a much more highly fermentable wort because you're making all those little maltose molecules that the yeast like to consume. And if you're on the higher end of the spectrum, then you're going to be in the range for alpha amylase. And so you get better efficiency, but like kind of lower fermentability. And then limit dextrinase plays kind of a smaller role, but is also involved there. There are also exogenous versions of these things that you can add. So the ones we were talking about before, the ones that are inherent to the brew process, and then there are ones that you can buy to kind of aid, depending on what direction you want to take your beers. The equivalent of alpha amylase, you can actually buy alpha amylase that's been purified from either fungus or a bacteria. And a lot of times the macro guys use these for low calorie and light beers. It's a common additive for that. Beta amylase actually doesn't have a commercial enzyme equivalent that I'm familiar with. If anybody knows of one, please let me know. There is a limit dextrinase out there called polylinase. Polylinase is a chain of maltotriose molecules. That's not that common to be used, but that's one that's out there. And then one that I think people use a lot, and perhaps is the one that they're most familiar with, is amyloglucosidase, which is also known as glucoamylase. That's something like your Amylo 300 from BSG, one of those kind of things. Obviously, when brewed IPA was a thing, that was something we all became really familiar with. It's also used in making light lagers or low-calorie beers, and then also saison-like beers. So if you wanted to, for example, make a saison with something styleless, whether it was a styleless saison strain or whether it was like a Belgian strain, for example, that you were trying to dry out a little bit, adding something like glucosidase would be a great way to go. Obviously, all of these things are breaking down starches into sugars, but each one has a specific effect, so you can't just chuck in one and expect to be getting the same result. They all kind of have different places that they like to cut on the starch, and that's because all of these enzymes have very specific targets. I think we talked about, or maybe you've read about the idea that alpha amylase, for example, breaks down these 1,4 linkages, right? Or like beta amylase can do 1,4 linkages in a certain place. I kind of wanted to go through what that meant. I had to remind myself about how carbon numbering worked. I took Orgo 25 years ago, and so remembering all this was kind of a stretch. But this is a glucose molecule, and that carbon is number 1, and it goes around in a circle, and then this one up here is number 6. So when you talk about these different linkages, all it really means is which parts of the glucose are attached to each other. So as you go across here, you've got the 2 ends that are attached, and so that's the 1 to the 4. And then when you end up on the break like this, then you get this like 6 molecule attached to a 1. So that's what a 1,6 linkage means. I thought this was just something that was interesting so you actually could visualize what those numbers meant. Because sometimes I read past them and I'm like, 1,4, 1,6, it's all the same, it sounds kind of similar. That's actually what it's talking about. There's also enzyme product specificity, and by this I mean enzyme manufacturer specificity. I had started to do some experiments on amyloglucosidase, and I was surprised to find that the recommendations from the manufacturers on what should be the same enzyme are very, very different. So even though it's marketed, they're both amyloglucosidases or glucoamylases, you can have different effects based on which amyloglucosidase it is. So if it came from a different organism, it might have a little bit of a different amino acid structure and might behave a little bit differently. Or it might have different pH ranges or temperature ranges, or they might have, if the manufacturer purified it in a different way, it might be a different concentration. So definitely pay attention to your manufacturer's recommendations, because like for example, if you look at the pH, here this one can go all the way down to 3.5, but this one bottoms out at 5.2. So if you think you have this one, but you went and bought this one because they were out of stock one time, just know that like you really need to pay attention to what you're buying. Yeah. Also the idea that like one doesn't have any kind of a time range, one takes 1 to 4 hours. Just keep an idea of what you're looking at. Some other categories of enzymes that you can use during the mash are things like proteases, peptidases, glucanases, and xylenases. Proteases and peptidases are just there's words for things that break down proteins. There are tons of these. They're involved in fan release, clarity, and head retention. Beta-glucanase is maybe one of the most popular enzymes that you can buy. It's for breaking down beta-glucans, and we all kind of know those can have a major increase in viscosity and can gum up our mash. And so by adding beta-glucanase, you can help with filtration improvement and extraction efficiency. Xylenase is kind of a similar thing. Xylens are sort of like glucans in that they're big long-chain sugars, but rather than being made up of glucose, they're made up of xylens, which are a 5-carbon ring. And same thing, decrease the work viscosity, increase your runoff rate. So this is sort of a diagram of what those are. I'm about to lose a cord here. Proteases and peptidases, like I said, are just things that break up amino acids. Lots of different kind of categories here. You can buy different kinds of enzymes that do this kind of stuff. They come in a couple different categories. One is endoproteases, which cleave inside the amino acid chain, and exoproteases, which kind of chomp from the end. Take a look at what different kind of manufacturers have. It depends on what you're kind of looking for. If you want to increase fan, like I said, if you want to improve clarity or head retention, there's all kinds of different enzymes out there that do those kinds of things. And then also same idea with like the beta-glucans and the xylans. It's very similar to sort of the idea of these saccharification enzymes, except for you're probably leaving bigger chunks. So this is what a beta-glucan from barley looks like. It's got 1,3 and 1,4 linkages, so it kind of like forms these different chains that then they all interact with each other. When you get water and you get a big gel and it's a pain in the butt. Xylans do the same thing, and so you can add exogenous enzymes to take care of those problems. All right, so now we can move on to enzymes that are used during fermentation. They also are going to be involved in attenuation of your beer, clarity, gluten reduction, involved in different aroma aspects, and also in souring. So we're kind of going to go through all of these different categories. Some of them we've already talked a little bit about the enzyme itself, but use it at different times, so things like amyloglucosidase. And then we'll also go through some other exogenous enzymes, and then get into some of the ones that you can actually buy a yeast that expresses them. So one of the ones we've talked about that you can add in the mash, you can also add during fermentation. That's these amyloglucosidases or glucoamylases. They cleave glucoses from the end of the molecule. One of the big things is if you use this in the mash, obviously it's killed off by your boil step. If you use it in the fermenter, which is one of the ways that they say that you can use it, you have to keep in mind that that's going to remain active in your beer. So make sure to pasteurize afterwards in order to denature your enzyme. Otherwise, you can get what I think we still call bottle bombs, even though they're cans. I don't know if you guys have a better word for that. Definitely also don't pitch your yeast from this, because you can have it carry over from batch to batch.
Gushers.
Pardon?
Gushers.
Gushers is a good word. Yeah. Not as violent. Maybe that's nicer though. Like I kind of was telling you about, I was doing some experiments on the amyloglucosidase just to kind of show its effect and kind of figure out different places where we can use it. So this is an example of like the effect of how effective amyloglucosidase can be. These on the left are some control strains where we've taken a Saison-like strain or something that has sta. So 039 is our beer de garde. 200 is Sactois. I think we call it Tropical IPA. And we created styleless versions of those. So as expected, this was a relatively unfermentable wort just to kind of show this effect more strongly. You can see the dark versions are the wild type and the lighter versions are the ones that don't have sta. As you would expect, the ones that don't have sta don't attenuate as well because they can't cleave off those sugars and the yeast kind of give up because they're so used to having glucose all the time. If you add a dry hop, you can get creep, and that's one way to kind of dry out these styleless beers. So you do see a reduction, but not as strongly as if you add something like amyloid glucosidase. Those Saison-like strains really like just straight up glucose, and that's what this enzyme provides. So just an example of like how effective amyloid glucosidase can be. There are also enzymes during fermentation you can add to increase your clarity and decrease your gluten content. You guys are probably most familiar with things like, if they're brand names, things like Clarix, Clarity Firm, or Beet Clear. There's lots of other ones out there. Those were just three that I knew off the top of my head. The way this works is that gluten is actually made up of both gliadin and glutenin. When you get them together, they form what's called gluten. And gluten is high in the amino acid proline. So proline is just a big chunky amino acid, and these endopeptidases go after all the proline and break it up. So that's the reason that works. It also means it's going to digest anything in the cell that has proline, but proline's kind of a weird one because it is so chunky. It tends to mess up some different proteins. It tends to make the structures kind of unfold, so these yeast cells don't use it that often. So it is going to break down anything that has proline, but specifically what tends to get broken down is gluten. The uses for that are so that you can make gluten-reduced beer, reduce your maturation time, increase your colloidal stability, so that's like a reduction in chill haze because it breaks down the proteins involved in that as well, and then also improve foam stability. So it creates the right size peptides to actually create the head on a beer, so the things that like make the bubbles. Then you can add exogenous beta-glucosidase. That is an enzyme that is involved in biotransformation. Specifically, one of the key ones is the transformation from this geraniol glucoside into geraniol. So you take a non-aromatic molecule, and then by cleaving off this glucose, you end up with an aromatic molecule. So this geraniol, which is kind of like a rose flavor. That obviously then gets processed into additional flavors, so linalool, citronellol, things like that. So you can get beta-glucosidase through an exogenous process. There also are strains that are higher in beta-glucosidase, so if you're looking to push biotransformation, your strain choice matters. So that's one case where you can use either yeast-derived or exogenous enzymes. Another aroma enhancer are carbon sulfur lyases. These are the enzymes that are in thiolized beers. There's lots of different names for these enzymes. Carbon sulfur lyases, beta lyases, people call them CSLs. They're all kind of the same class of enzyme. What they do is they take, again, a non-aromatic precursor. So in this case, it's a thiol, which is this bottom part here, attached to an amino acid cysteine. And the beta lyase just cleaves that off and creates this free thiol. I'm assuming you guys have heard all about this because we have all these strains. I should say that we're not the only ones out there who have thiolized strains. Berkeley also has a genetically modified strain. There are other people that are also marketing them, but are the ones that are genetically modified are way higher expressing for all of these enzymes, so you get a higher thiol output. They're the characteristic flavors in things like Sauvignon Blanc wines. They're also tropical and citrus aromas, and they're super potent. The reason I'm getting into this is because different enzymes create different levels of this. So just an idea, these are odoractive in the parts per trillion range. So if you take the metaphor of like an Olympic pool, you only need to have like a droplet in the Olympic pool for you to be able to sense it. So they're very, very potent. We use a couple of different carbon sulfur lyases. One is called IRC7 and one is called PAT-B. IRC7 is what's in our lower expressing ones, so Cosmic Punch. It was actually derived from Chico, so it is a yeast. The origin for it is actually a brewing yeast. PAT-B is a bacterial enzyme that we put into all of these different backgrounds, and so they have a much higher expression. And so that's just something to kind of to realize, is that the expression level and the enzyme activity can really affect the output. So the Cosmic Punch, you end up at about 10 times sensory threshold, but things that have Pat B in them, you're at about 300 times sensory threshold. So much more intense levels of thiols, and that's all because of the choice of enzyme in those different yeast strains. Threw this in here just in case anybody wanted the slides at the end. There's lots of other ways to dial in thiols that you can come and ask me about if you want. Another aroma enhancer that is actually expressed by the yeast is ALDC, or alpha-acetolactate decarboxylase. So I think about this as an enhancement of aroma because you're getting rid of a bad flavor. So in this case, the ALDC prevents formation of diacetyl. And the way that it does that is there's a pathway in the cell where it's actually for creation of these two amino acids, valine and leucine. And you take a precursor for that product that would leak out of the cell, spontaneously turn into diacetyl, and then come back inside to become acetoin. And you basically bypass that. So we go straight from alpha-acetolactate. ALDC takes it right into acetoin, which is a flavorless molecule. So you bypass this diacetyl step. Like I said, it doesn't actually reduce diacetyl levels, just prevents the formation of diacetyl. So it does mean that if you have yeast management problems, that's the only thing that it's going to deal with. It's only going to deal with your diacetyl. If you are doing bad things with your yeast, you're still going to get out, acetaldehyde and all kinds of other off flavors. But ALDC can prevent the formation of diacetyl. Times when you would use that are when you have strains with elevated diacetyl production. Things like in lagers, so that you can get faster turnaround, because one of the main things for determining when you're going to crash is if you cleared your diacetyl. Or in dry hop beers, so it can help prevent the formation of diacetyl that comes along with hop creep. We have a lot of different versions of these. Other makers do also. But yeah, you can check it out. They can make almost any kind of beer with these ALDC strains. And what's cool about them is that your diacetyl levels remain below threshold for the entire fermentation. So this is an example of our German lager. Just the wild type, you get a big spike, and then it clears it out over time. This is also being compared to adding exogenous ALDC, so ALDC from a bottle, and then this ALDC expressing German lager. And you can see in both cases here, the ALDC does its job, whether it's added from a bottle or whether it's added by adding the yeast. However, that's not always the case. There are a couple times when you want to be careful about if you're adding ALDC from a bottle versus using an ALDC strain. So we're, in this experiment, looking at a couple of different scenarios here. The first is a strain, the wild type strain with a dry hop, the wild type strain with a dry hop, and an ALDC addition at knockout, so right when the beer goes into the fermenter. One that has a dry hop and addition at day 7, and then this is actually our ALDC expressing version of Chico. So the first thing that I want to show you is at day 7, before you add the dry hop. This is just the state of where day 7 is. You can see that these two, we're going to call those about even. Those are two states that don't have ALDC added. And then this one right in the middle is the one that had ALDC added at knockout. So you can see it's doing its job. It reduced the diacetyl a lot from day 0 to day 7. And then the one that actually expresses it internally is way below threshold. So you're doing kind of what you expect. But then after the dry hop, you can see, as you would expect, the one that has no ALDC is the highest. The one that had the knockout addition of ALDC is a little higher. And that's kind of because as the beer ferments, you get further and further out of the range of the comfortable range for that enzyme, and so it starts to degrade. Also, just over time, it gets consumed by the yeast, and it gets stuck to the cell walls and things like that. Which is why a lot of people, when they add ALDC, they add an additional shot of it at day 7 with the dry hop, and you can see that one is doing fairly well. But after an additional 7 days of fermentation, they kind of start creeping up because they can't keep up with how much diacetyl is being produced. But the one that had ALDC inside is still low. So lots of different ways to deal with it. I think you can be successful with ALDC that you purchase and add. You just have to be very cognizant of when you add it. And then the last thing I wanted to talk about was yeast that express lactate dehydrogenase, so LDH. These are souring yeast. We have a strain called Tartango, but there's lots of other ones out there. There's Philly Sour, there's Sour Viciae, things like that. What this does is it takes advantage of a bacterial enzyme LDH that can take one of the precursors that's in the alcohol pathway. So you go from sugars into pyruvate and you end up making ethanol. It can take some of that pyruvate and push it towards making lactic acid. So that means that you can make sour beers in the fermenter. It's great because you can also dial in your lactic acid expression. So depending on what Plato wort you start with, you can get higher or lower levels of lactic acid. So because you're taking the sugars that were involved in ethanol and pushing them towards lactic acid, you're going to get a little bit less alcohol than you thought you were going to. And you can take advantage of that by, like, if you have a high Plato wort, you'll get high levels of sourness. If you have a low Plato wort, you'll get low levels of sourness. So it's a good way to kind of dial that in. Just as an aside, I was talking to a couple of you guys about this lactic acid expressing yeast today. One of the things we tried to do was have a little bit of a lower expression level than some of the ones that are out there. So just a plug on our part, which I apologize. I'm trying not to do too much of that. But you can actually repitch this one, which is kind of nice. So cool. So at that point, go through a couple conclusions. Lots of different reasons to use enzymes. They can enhance quality and efficiency, so you can optimize your extraction. They help in filtering your mash. You can help minimize haze, prevent diacetyl formation, and they also let you do cool new things. So that you can make gluten-free beers with alternative grains, create thiol beers, like create flavors that you've never seen in beer before, and brew sour beers with this lactic acid producing yeast without having to do kettle sours or add some kind of exogenous acid. And with that, I will close up. Thanks for having me here, and if you have any questions, I'm happy to take them. Any thoughts? Yeah.
Have you done going multiple generations to see how, when it starts to degrade, like the decay rate, you see that it starts to be less effective as it gets later on?
Pretty deep into generations. One of the main things that we wanted to make sure happened was, that you had health with repitching and that you weren't interfering with any of that amino acid synthesis. So we grew it on various media where you didn't provide those amino acids. We did situations where you provided extra of those amino acids just to make sure that there were no differences in kind of how the yeast were growing, and all of those were fine. So it seems like we're not messing with that pathway in a way that is meaningful to the yeast. We've taken it over multiple generations, and it's been fine. We don't really hear any complaints from anybody. So yes, we have done that, and it seems to be healthy. Cool. Well, I appreciate you guys listening. Thanks.